All right, so this is Rutherford's gold foil experiment. The main reason for doing a video like this is that a lot of the stuff that's out there, while mostly correct, does have a few misconceptions, common misconceptions that are quite widely spread through a lot of the websites and textbooks and things like that, and even in past NZQA exams. There's a bit, so I wanted to just make it clear what those things are. So Rutherford's gold foil experiment was the experiment that gave us the simple model of what we kind of understand of the atom now, with a nucleus and electrons orbiting around it. Now, the experiment is commonly referred to as the gold foil experiment or gold leaf experiment, where there was a alpha particle beam. Alpha particles and the important properties of alpha particles in terms of the experiment are that they're positively charged, they're quite heavy for particles, and they're fast moving. That means they have quite a lot of momentum, and it takes quite a strong force to deflect them. The gold foil that they were aimed at was a few hundred atoms thick, so quite thin in an atomic sense. It was thin enough so that any deflections that were caused could be considered to be interactions with a single atom and not like the aggregate of several interactions with different atoms. And the entire thing was done in a vacuum because alpha particles are quite easily absorbed by air. So they had to remove all the air so that there were no absorptions, or even more importantly, any of the deflections that were caused were due to the gold foil and not due to the air that it was passing through. So around the gold foil there was a fluorescent screen that anytime an alpha particle hit it, it would emit a flash of light. And basically they spent the Rutherford and his students basically spent a long time painstakingly counting flashes of light. They would count how many flashes of light appeared in a particular area in a minute, for example. And by that they could, from that they could gather like information about where the particles went, where the alpha particles were going. So the first observation they made is that most of the alpha particles were undeflected or deflected only slightly, which is what they were expecting to find. Because what they were doing this experiment for was to try to verify Thomson's model of the atom, which they expected only slight deflections. But being a thorough experimental physicist, Rutherford decided just to check everywhere else just to make sure. They made a second observation that there were actually a small number of alpha particles, only very few, being deflected quite a large angle, which was an unexpected result. They didn't expect to see large deflections. And even more unexpected, was very, very unexpected, was some of the alpha particles were being reflected back. Rutherford is recorded of having said that this was, it was so surprising, he described it as being like firing a 15-inch shell at a piece of tissue paper, and the shell bounced off the tissue paper. So 3 observations: most of the alpha particles were undeflected or deflected only slightly. Secondly, a smaller number of them were deflected at a large angle. And a third observation, a very small number of them were deflected, reflected back the way they came. Now, the common textbook explanation for this is that each of those observations can be explained by some property of the atom. So the fact that most of the alpha particles were undeflected, that means that most of the atom is empty space. Okay, so the alpha particles are just going straight through and they're not interacting with anything, so they're undeflected. Some of the small deflections are they're passing vaguely nearby something that might be deflecting them, but there's mostly nothing there. Some of the alpha particles being deflected at large angles, the second observation, is an indication that there is a central mass in the atom which must contain most of the mass of the atom. The reason for that is that the alpha particle, like we said before, it's relatively heavy and quite fast moving. It's got a lot of momentum, so it needs quite a lot of force to deflect it. But there's no noticeable recoil of the gold foil. So the thing that the alpha particle is bouncing or is being deflected by must be significantly heavier than the alpha particle. And we already know that it must be very small because most of them are undeflected. So there's a small central mass which contains most of the mass of the atom. And the third observation, that some of the alpha are reflected back, and this is the problematic one. That's commonly said that this means that the central mass must have a positive charge, or it contains protons, because it's repelling the positive alpha particle. But the logic, now, while that's true, the statement that the central mass is positive and it contains protons, that's not actually that can't actually be shown from this experiment, because this could be explained in two ways. If we take a positive alpha particle, such as this, which is being reflected around in some way, sort of being deflected back. Now, a reflection could be achieved in two ways. It could be either a positive charge and it's being repelled back, or it could be a negative charge and it's kind of attracting it, sort of like slingshotting around it, but like sort of like a meteor going around a planet or something like that. So that the fact that you're getting those reflections back, because it could be either a positive or a negative charge causing that, you cannot actually make a conclusion about the nucleus being positive or negative from the fact that the alpha particle is being reflected. Okay? So why didn't Rutherford just say that? Well, the fact is, he actually did say that. He was very clear in the paper that he wrote about this, The Scattering of Alpha and Beta Particles by Matter and the Structure of the Atom, Ernest Rutherford, Philosophical Magazine, May 1911. Great read. Get amongst it. A few quotes from that one. He actually said, this is right at the start of the paper, the main deductions from the theory are independent of whether the central charge is supposed to be positive or negative. For convenience, the sign will assume to be positive. So he went through the rest of the paper explaining it as if it was positive. It seems fairly clear that he thought the nucleus was positive, but he was very careful to be clear about what he thought and what he could prove, or what he knew from the experiment, what can be concluded from the experiment he had done. He also, again, said later on, it has not so far been found possible to obtain definite evidence to determine whether it be positive or negative, referring to the nucleus. So Rutherford was very clear that from this experiment, you cannot actually tell whether the nucleus is positive or negative. Okay? Other experiments done later came to that. So what can you actually conclude from this? So this is the same as before with the same observations. So observation 1, most alpha particles are undeflected or deflected only slightly, which was expected. That tells us that most of the atom is empty space, okay, which was the same as we had before. The second observation, that a small number of alpha particles are deflected at a large angle, that tells us that there is a central mass that contains most of the mass of the atom. Okay, that the alpha particle with a lot of momentum must be being deflected by something very heavy, because that there is no noticeable recoil of that gold foil when it's deflecting these alpha particles. And the third one, a very small number of alpha particles are reflected back, doesn't tell us that it's positive, but what it does tell us is that the central mass has a strong electric field, which means it must have a very concentrated charge. That means in order to reflect or deflect an alpha particle back the way it came, it needs a very strong electric force. And that's either a very strong repulsion from a positive charge or a very strong attraction to a negative charge. Either of those could have that effect. Either way, you must have a very concentrated charged region inside that atom that is causing that alpha particle to be deflected back the way it came. So this is, I think, a better summary of the conclusions of the gold foil experiment. So most of the alpha particles are undeflected, tells us that most of the atom is empty space. We don't argue with that one. The second one, some of the alpha particles are deflected at large angles or are reflected back. So I've kind of combined two observations there. That tells us two things. The central nucleus contains most of the mass of the atom because there's no noticeable recoil of the foil. And secondly, it tells us that the nucleus must have a strong central electric field caused by a concentrated charge. A strong electric force is needed to deflect the fast-moving alpha particle. Now, when you combine this with one of the observations from earlier experiments, such as from Dalton and Thomson, both had this condition that the atom is neutral. If you have a strong central charge, but the atom is overall neutral, that must mean there are small, lightweight particles of the opposite charge orbiting that central charge. So you've either got a very heavy central positive charge with very lightweight negative charges orbiting it so that it's overall neutral, or you've got a very heavy, strong central negative charge with very lightweight positive charges orbiting it. And he was very clear that you couldn't tell which of the two was the case from his experiment. It seems pretty clear that he thought it was a very concentrated positive charge with negative charges orbiting it, as we now know. But he was very clear that you couldn't tell that from the gold foil experiment. So there was no conclusion of a positive nucleus, and there was no mention of protons. Rutherford was also very clear that the structure of what's going on in that nucleus, he had no idea from this experiment. Okay? All he was saying was there is a nucleus. He did not say there was protons, and neutrons were not discovered until decades later. So the structure of that nucleus, Rutherford made absolutely no conclusions about it. And just a quote from Rutherford, if your experiment needs statistics, you ought to have done a better experiment.